Now we discuss a surprising difference between the complex exponential and the real exponential. Namely, the complex exponential is not a one-to-one function on the whole complex plane. We remember that the real exponential is one-to-one. It's always positive and it's strictly increasing. But with the complex exponential, we have the following. E to the z is equal to 1 if and only if z is equal to 2 times pi times I times k for k in the integers. In other words, the single number 1 has the infinitely many preimages 2 times pi times I times k under the complex exponential. Let's prove it. We'll do the reverse direction first because it's easy, it's just a direct calculation. E to the 2 times pi times I times k. This is I times the real number 2 pi k, so Euler's formula tells us it's cosine of 2 pi k plus I times sine of 2 pi k. And then real trig says cosine of 2 pi k is 1 and sine of 2 pi k is 0. So there we go. What about the reverse? Say we have z equals x plus iy and e to the z equals 1. Then we get 1 equals e to the x plus iy, which is e to the x times e to the iy. And we solve for e to the iy equals e to the minus x. And then use Euler's formula to write that as cosine of y plus I sine of y equals e to the minus x. And remember, our goal is to show that we must have x equals 0 and y equals 2 pi k. So if we take the imaginary part of both sides in the last equality above, we get 0 equals the imaginary part of e to the minus x, and that's because e to the minus x is a real number. And that, by the equality above, is the imaginary part of cosine of y plus I sine of y. And cosine of y and sine of y are real numbers because y is real. So that imaginary part is just sine of y. And so I have sine of y equals 0, so y has to be 2 pi k for some integer k by properties of the real sine. So far so good. What about that x? Well, if I take the modulus of both sides of that last equality above, I get modulus of cosine of y plus I sine of y equals modulus of e to the minus x. The Pythagorean theorem tells me that modulus of cosine of y plus I sine of y is equal to 1, and e to the minus x is a positive real number, so its modulus is e to the minus x. So I get 1 equals e to the minus x. When does that happen when x is real? Only if x equals 0. So z is equal to x plus iy, which is equal now to 0 plus I times 2 pi k, which is 2 pi I k as desired. The complex exponential is not one-to-one. More comfortingly, we have the property e to the z is non-zero for all complex z. So whatever e to the z is, like the real exponential, it can never be 0. Let's prove this by contradiction. If we have e to the x plus iy equals 0, then we just have 0 is e to the x times e to the iy. And so if we take the modulus of this, we get 0 is modulus of e to the x times e to the iy. And that modulus is e to the x, because e to the x is always positive, and the modulus of e to the iy is 1. So we have here 0 equals e to the x. Is that ever possible? No. E to the x is never 0 when x is real. E to the x is always positive for real x. So proof by contradiction works. Last, if w is a non-zero complex number, we can always solve the equation e to the z equals w. In particular, this equation has infinitely many solutions. E to the z is equal to w if and only if z is equal to the natural log of the modulus of w plus I times the principal argument of w plus 2 times pi times I times k for k an integer. To be clear with this natural log with the symbol ln, I mean the real natural logarithm, I mean the inverse of the real exponential. In a subsequent video, we'll talk about extending the logarithm to complex numbers. But because w is non-zero, the modulus of w is always a positive real number, so natural log of modulus of w is always defined. Let's prove this if and only if statement. We'll do the reverse direction first because it's easier. Let me calculate e to the natural log of modulus of w plus I times the principal argument of W plus 2 times pi times I times K. So this is e to the sum of three things. I'll write this as a product of three things. E to the natural log of modulus of W, e to the I principal argument of W, e to the 2 pi ik. So the first factor, e to the natural log of modulus of W, e and natural log cancel each other out for real numbers, so I get modulus of W. E to the I times the principal argument of W, well, not much I can do there. That's e to the I times the principal argument of W. E to the 2 pi ik, that is just 1. So I'm left with modulus of W times e to the principal argument of W times I. I know that is W from polar coordinates. So the reverse direction is proved. Now we'll do the forward. Suppose we can write z equals x plus iy, and we have the equation e to the x plus iy equals w. Well, that we know is modulus of w times e to the I principal argument of w. W is given to me, I want to solve for x and y. So if I take the modulus of both sides, I have modulus of e to the x times e to the iy equals modulus of w e to the I principal argument of w. This is just going to knock off those complex exponentials. So I get e to the x equals modulus of w. W is not 0, so modulus of w is a positive number. I can solve for this uniquely as x equals natural log of modulus of w. Now I substitute this back in, and I'll get e to the natural log of modulus of w e to the iy equals modulus of w times e to the I principal argument of w. Okay, e to the natural log of modulus of w is just modulus w. Let's knock off the modulus w's from both sides, and I get e to the iy equals e to the I principal argument of w. So now I just have an equation involving y. I can rearrange this equation into saying e to the I times the quantity y minus principal argument of w equals 1. But on a previous slide, we showed what happens when e to the z equals 1. What do we know about the exponent then? We must have I times the quantity y minus principal argument of w equals 2 pi ik for an integer k. So we divide off by I, and we get y equals principal argument of w plus 2 pi k for k an integer. So we have solved for x equals natural log of modulus of w, and y has infinitely many values, principal argument of w plus 2 pi k.